Hey friends, welcome back. This is lecture number 20 for CSE 1322. Today's lecture is going to be a relatively short one. I'm just going to finish up the topics about parallel processing and talk at a high level about some additional stuff that we didn't talk about in the threading lecture last week, or earlier this week. So this is the end of module number 8, and from here on out we're going to move into data structures for the remainder of the semester, and we're almost there, so that's the good news. If any of you are wondering about getting back your results on test number 2, you should be getting that back sometime this week, with any bit of luck, probably Wednesday. It might be as late as Thursday or Friday, just depending on how things go, but the tests are substantially graded at this point, so I would expect that you'll have access to them in grade scope very shortly. Okay, so today's lecture is about parallel programming. And the thing I want to say here first is that in most universities, this is an entire class. So let me be clear that at the end of this lecture, you're probably going to be scratching your head a little bit and going, that was kind of high level. Was I supposed to get something decent out of that? The answer is we want you to understand at a high level how parallel processing works, but we simply don't have enough time to go into all the details of how that works in this class. So I'm going to give you a high level overview. You're going to be tested only at a high level overview. We're not going to ask you to go off and do very crazy things. In your lab, you will probably have to write something similar to what we're doing in class, but it shouldn't be too difficult. So all right, so without further ado, let's talk about why parallel processing is a thing and why it is that we might want to care about it. The general idea is that it's a way of speeding up programming. As I said in the last class, most computers that you buy today have more than one core or more than one processor. To be clear, when I say more than one processor, a machine can have two physical processors, and each of those processors can have multiple cores. So the total number of available processing cores is number of cores per CPU times number of CPUs. Today, most computers have one physical CPU, and then it may have some number of cores, but it is possible to have multiple physical CPUs as well. So all of this comes from Moore's law. You hear this tossed around a lot. Basically, the idea of Moore's law is that every 2 years, the speed of your processor is going to double. And that was really true for many, many years. As this slide says, that happened for about 50 years. The reality is we ran into some problems from a processor design. Eventually, the processors got to be so small that the distance between the individual parts, the logic gates effectively, got to the point where we really cannot make them any smaller. Every 5 or 6 years, the major chip manufacturers figure out how to get it down another nanometer, but it really doesn't make as much of a difference as it once did. The second problem is heat. As you get more and more electrons flowing through more and more gates, you end up causing more and more resistance through the processor, which makes the processor get hotter. So actually, probably the biggest problem that we have with processor design is heat dissipation. In a very small device, you have a massive amount of heat that's being generated. So that's why if you look inside your computer, on top of your CPU, you will find a large heat sink, which is to dissipate a lot of the heat, and then a very big fan sitting on top of that, or maybe it's water cooled in order to try and pull that heat off as fast as it can and blow it out the back of your case. So the bottom line here is that processor speeds are not going to increase dramatically from here on out. They will continue to increase, but it won't be nearly as dramatic as it used to be. So as a result, the ability for us to just say, we'll wait on the processors to get faster is really not a good plan anymore. So instead, what the manufacturers of CPUs have done is that they've started to put more and more cores onto the single processor. And then it's up to the developers to write their code in such a way that it utilizes those cores, which is done either through multi-threading or multi-processing. So parallel computing or parallel processing basically boils down to splitting up your program in a way that you can break it up onto different processors. But there's huge problems with doing that, and that's why there's an entire class about this. There's only some stuff that can be parallelized. When I took my software engineering class a million years ago, one of the books that we had to read was something called The Mythical Man Month. And the reason for this book and the basic premise of the book is, in your head, if I told you that I need you to paint this room that I'm sitting in, and I told you that I know the last time that I painted this room, it took me 12 hours to paint it. Then if I told you I'm going to give you a crew of 10 people, how long will it take them to paint the room? in your head, you would logically say, well, if it took you 12 hours and you're doing 10 people, then you should get it done in 1.2 hours. Because the 10 people can independently paint one little bit of the room, and in 1.2 hours, they'll be done. And that sounds great in theory, but in actuality, that's not how it works. Because the first problem is you've got to split up the paint. You have to have enough paint and rollers in order for everybody to be able to paint at the same speed. And there are just places where they're going to get in each other's way, and it's not going to be physically possible for two people to be working on the same project at the same moment. So, in a very high level, parallel processing definitely speeds things up. But once you get into the detail of that, you're going to realize that a lot of jobs that you do cannot be parallelized very well. If you have something that requires calculating one answer, and then you need that answer for the next step, you can't parallelize. You have to do the first step first and then move on to the second step. It doesn't matter if you have 100 cores available, it's still going to take the same amount of time. And so you have to be careful when you talk about parallelization that you're not saying that everything is going to be, if you have 2 processors, it's going to be half the time. If you've got 4 processors, it's going to be a quarter of the time. That's not really how it works. It's probably going to be a 30% increase in speed, a 40% increase, depending on how parallelizable it is. So keep that in mind. The second thing is that as you're working with data, you have times where there's multiple people who need the same data at the same moment and maybe need to be able to write to it. And again, I think in the last example, I gave you the bank example, where if you both go and you try to withdraw money out of an ATM at the same moment, we have to lock the balance number and only allow one of those threads or processes to change that number at any given moment. So as a result, while that number is locked, the other process is just sitting there waiting. Again, throwing more CPUs at it doesn't make it go any faster. So the point that I'm bringing up here is you're going to sit in an interview somewhere and somebody's going to ask you, you have this job, make it go twice as fast. And your default reaction might be to parallelize it. And that probably is a good idea, and I'm not in any way saying you shouldn't do that. But you need to understand that it probably isn't going to give you a 2x performance increase just because you have 2 processors. Okay. And I think all of that is what I just said. In the C# language, the task parallel library, or the TPL, is what you're going to use for task parallelization. And the good news is that back in my day, when I had to learn all this, you had to do it all manually. Nowadays, there's built-in things into both of the languages that allow you to just say, this is parallelizable, please go process it in the best way that you can. And then it's up to the language to figure out how to break that up and how to use it. So the task parallel library scales based on how many processors are available. So you write the code, you specify which bits are going to be parallelizable, and then it decides how it's going to break it up, whether it's on 2 cores or 4 cores or 100 cores or 1,000 cores or whatever it may have. Without you having to make any changes to the code, it will decide the best way possible. You can pass it a hint as to how many threads or how many processes you think you wanted to do. You just got to be careful with stuff like that because, again, if you tell it that it has the ability to break it up into 1,000 processors, but you actually only have one processor, all of the overhead of doing all of the work to synchronize all of the threads or all the processes actually will slow you down. So telling it you have more processors than you have is not a good idea. It will actually probably make it run slower. And again, to be 100% clear, there is a cost to parallelization. There's a cost in the language of breaking it up and managing all of this, and then that by itself may make it so that even though you gain from having more than one processor, you actually may end up losing some of that gain because of the overhead of taking care of all of the different processes and whatnot. Okay, so if we have some job that we want to do, normally you would have used a loop, a for loop or a for each loop to run through it and to find your answer. We have a new method called parallel for each, which allows us to do a parallelized version of a for each loop. Again, you can only use this if everything that's happening inside the loop is 100% independent from everything else that's happening in the loop. So I'm just going to break out of the slides here, and I'm going to go over to a Replit window. And again, you can grab the URL from the top if you want to go play with this yourself. So what I'm doing here is I did it all in the main class. I'm not doing anything fancy. I started off and I defined a size variable, which I set to 1,000,000. All right, and then I created an array of integers of that size. So I have a 1 million cell array. This method here just picks random numbers and fills all million cells of the array with random numbers. Each number is going to be a number between 0 and 100,000. So very random junk, basically. And then I have something where I would have searched linearly. And what I meant by that is, without using any form of parallelization, I want to go through the loop and I want to see if a particular target is in the array. So again, to be clear, we generate a big array, we put random numbers into all of the cells, and then I'm able to use this search function to check and see if a particular integer is in that array. This is not very useful code, I totally get that. But if we call search linear, it's going to walk through every cell of the array, and if it ever finds the answer, so if the array at position j is equal to the target, it returns true. If it gets all the way through the loop, it returns false, so we know whether we found it or not. All right. I'm then going to show you the parallelized version of that. But before I do that, let me just run the serial version so that you can see that it does actually work. And I'm just going to turn off the parallel version. Okay, so run, and we're going to generate a million cells, and we're going to walk through looking for the number 19. Why 19? Because I said so. I don't know. It doesn't matter. It's a random example. So you can see that, yes, I'm getting a warning about a result being created but never used. But ultimately, it runs and it says it found it. If I run it again, maybe it'll find it, maybe it won't find it, who knows. It found it again that time, so there was a 19 in there, and it found it again. Matter of fact, let's just modify that a little bit and have it print out the cell in which it found it, just so that we can prove that this is actually doing something. Also, I did it in the parallel version, so it's nice to do it here. All right. Found it in cell plus my variable for my loop here is j. All right, go. All right, so it chokes through and it found it in cell 23,372 that time. Next time we run it, it found it in cell 2,606 even, 78,300, and so on and so forth. So this is a very inefficient piece of code. Also, it's completely pointless, but it is chugging away and doing it. This is single-threaded because I didn't specify that it can do anything else. So literally, one thread started at the beginning and said, is this it, 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 6,300 times, or maybe 100,000 times, and so on and so forth. Great. So how can we speed this up? Well, I'm going to turn off this code, and I'm going to call the other version, which does the exact same thing. This time, it takes in a 19, the same as before, but it's going to do it in a parallel, and it'll print out if it found it. Okay, so what's different about this? Well, there's really only one thing. Right up here at the very beginning, instead of calling for and doing a for loop, I use parallel.for, which in order to be able to call that, I have to include system threading and system threading tasks. And then its parameters are slightly different. So if you remember in a for loop, you start off with the initialization, and then you have the test, and then you have the increment. That's typically how a for loop works. Well, in this one, it takes in 3 parameters, and the third one's going to blow your mind just a little bit. The first parameter is the starting position. That's easy, 0. The second parameter is the end position. That's easy also. That's what I called array size. And again, that was just defined up at the top as being 1 million. It's what I also used to create the array. So this will go from 0 to 1 million. The third parameter is actually technically that. Now, there's a lot going on here, and let me explain what's going on. So the first thing that you have here is an I variable, and that's going to be my iterator variable, much like in a regular for loop where you would typically say int I equals 0, I less than 10, I plus plus, I is your iterator, and that's what's going through the array. So the same thing is happening here. I have an I, so that part's easy. The second thing that's happening here is a state variable. The state variable specifies whether or not the threads are running. And it is possible for me to stop all of the threads because they're all going to be running simultaneously. So to be clear what's going to happen when I run this, instead of it running a single thread that's going to check all 1 million cells, it is going to fork 1 million threads, each of which is going to look in one cell and return their answer instantly. So the speed of this is going to be much, much faster, assuming that you have enough processors to actually do all 1 million. If you had a million, this will all happen in a single operation. Boom, done. Answer generated. Whereas the previous one took a million operations. If you don't have a million processors, which you probably don't, then it's going to do it as fast as it can, but it's still much, much faster. If you're running this on a 16-core machine, then this is going to go in pretty close to 1/16th of the time. See asterisk footnote about all of the overhead and all the other things that could go wrong. But since this is such a trivially stupid thing, it actually probably will. I picked a job that's incredibly parallelizable. There is no dependency between looking at cell 0 and cell 1 in order for me to actually run through the code. So that's why I want to be clear about I'm being very careful about what I'm picking here. I'm specifically picking a job where I can actually do this all in parallel. Okay, so getting back to this weird syntax. I have I, which is my iterator, and I have my state variable, and they are wrapped in parentheses, and then there is an equal, greater than, and then there is an open curly brace with a bunch of code and a closed curly brace. Okay, I'm going to say this word, and you don't have to remember it, but the word that this is what's called a lambda function. Lambda, L-A-M-D-A. A lambda function is a function that you define that actually doesn't exist as a function. It only exists temporarily while it is running. So this lambda function, you will notice that normally when you define a method or a function, you would have a header at the top where you specify static void my header open parentheses int x comma int y close parentheses. Can you tell I've been grading a lot and that might have been the recursive one? But anyway, that header doesn't exist when you're dealing with a lambda function. As a matter of fact, this method has no name, which is weird. And it will only exist for the duration of this calling parameter. So this parallel.for will generate a method which doesn't have a name, which will float out in the ether. It will execute it, and then when it's done, it will destroy it and get rid of it. If you ever take an artificial intelligence class, you're going to see lambda functions a lot. There are a few places where you will run into them in other cases, and so it's useful to be aware of the fact that they can exist. You cannot just define a method without a header in general. You can only do it in certain circumstances where it's expecting a lambda function. And usually sort methods or things like parallel methods are examples where you might need to pass a block of code for it to use to do something in particular. And that's what's going on here. So again, this is called a lambda function. I want you to understand and recognize that a lambda function is a circumstance where you create something temporarily. It's basically a block of code, and as soon as it's done, it goes away and can never be called again. That's all you needed to get out of that. The syntax of this is that the third parameter that's coming into parallel for is this I, the state, and a lambda function of exactly what it is that you want the for loop to do. If you think about it in a weird way, when you do a normal for loop, there's kind of a lambda function, but it's not really a lambda function, that happens underneath the for loop, right? There's that curly brace and the closed curly brace, and everything that's in between executes over and over and over again. So you could kind of think of this as the same idea, but it is slightly different because this actually is a method. It's just a lambda method, whereas with the for, you're just really using the for syntax. Okay, if none of that made sense, please don't worry about it. This is not something that I want you to lose sleep over. I just want you to have heard the word, because you'll see it in documentation as you go forward in your career. And every now and again, you'll see something that says, you'll need a lambda function here. And I just want you to be able to say, okay, that doesn't sound too scary. I remember into talking about lambda functions. All right, so getting back to our code here. We are calling parallel.for instead of just for. We are passing the start number, the end number, an iterator variable so that it can be accessed inside of our little function down here, a state variable, which allows us to see what's happening, and then the actual lambda function, which tells it what it is that it wants to do. So inside this lambda function, I have if array at position I equals the target, then hit equals true, print out founded in the cell just like I did before, and then I'm calling state.stop. What's happening here? Okay, so in the other method, when I did it in the serial way, as soon as you find the answer, there's no point in keep looking, right? It's kind of like when you lose your keys in the morning. As soon as you find them, you don't actually keep searching the house, you just leave. So likewise with code, once you've gotten to the answer, there's no point in continuing the computation. And so in this for loop, I just very rudely called return. And as you know, a return in a regular method just exits the method immediately and returns the answer. So this loop was happily chugging along. The last time I called it, it was going to go 1,000,000 times, and it was on iteration number 3317 when all of a sudden I randomly called return, and that loop just exited instantly. In the parallel version, I can't really do that because 1,000,000 of these got started all together, and they're all chugging through their own code. So if I call a return, what does that really mean? It's not great, that's for sure. And the other thing that's weird is because this is technically a Lambda function, the return would only return this method, not the actual search parallel method, which is a parent of this method. Okay, so you don't want to use return. That's the key point. What you want to use is state.break or state.stop. There is a difference between the two. State.stop means I want all of them to stop. State.break just means I want no new ones to be created. Again, this is only a very specific circumstance. I wrote code that is going to very specifically allow it so that every single one of my parallel processes can chug away independently of each other, and this stop is going to declare across all of those processes, you can stop now, we found it. So in order for it to actually stop, all it does is it sets a variable. Each of the threads or each of the processes needs to actually check, do I need to stop? And if they do, then you can actually return out of each of the threads. I am calling return here, which will cause the thread to exit, but it's just that thread or that process. Okay, so now I'm going to go ahead and run search parallels because I think I commented back in. No, I'm not. I'm going to get some weird error. What happened? Oh, because I have random nonsense down here. Sorry. I was like, this worked a minute ago. How can it be broken suddenly? Okay, so it ran, and it did not find it. I'm going to run it again. Okay, so this time it found it, and you'll notice that we got a lot of output here, and I'm really happy that this happened because this is completely random. So some of the time this was never going to happen. So first thing that happened was it found it in cell 2693. Great. At that point, that process called state.stop. And you will see that there is at least one other thread that responded to that and died. As it turned out, simultaneously, another one, which was actually looking in cell 34,780, also found it at the same moment, and it would have also called stop, which was redundant because by that point it had already stopped, and that caused another one to die. Okay, so the reason I say that this is going to be random, first off, the random numbers, maybe we hit, maybe we don't hit, that was the same whether it was parallel or serial. But the order in which these executed, I have no control over. 1,000,000 processes got spawned. It was up to the CPU, the operating system, to decide which of those got the CPU first, which might have been cell 0, 1, 2, 3, 4, and 5. Or it might have been cell 0, cell 3158, cell 9243, and cell 7. Who knows? I think in Replit you're getting a single processor machine by default, and I think it's single-threaded. They only give you a very small amount of processing power. So in reality, this actually happened all in serial. The speed up of this would probably have been minimal. If I had recorded the time at the start and the end and I printed it out, you'd probably see that the serial and the parallel probably ran at about the same speed because there's only one processor. So it doesn't matter that it's all parallelizable. However, if there's multiple processors available, this version would have run faster. And the reason that you'll only ever see one or two dies is simply because there's only a small number of processors available. If you ran this on a machine that had hundreds of cores, or even a machine that had 16 cores, then you would see a lot of threads having to die because a bunch of them would have been running at any given moment, and as soon as one says, I got it, all of the other ones would die. So hopefully that makes sense. It's a very simple method. You realize that I didn't have to do anything crazy. I don't have to extend anything or invoke any weird objects or pass anything else in. I simply replaced a for with a parallel for, and then there was some crazy with the lambda function, but really that just meant I put weird parentheses in there and whatnot. You will note that the actual closing curly, or the closing parenthesis for this is all the way down at the bottom. There's a whole set of curly braces in between the open and close. This is all technically part of the header. And what I mean by that is I could have written this all on one single line. I don't, because I'd like to be able to read it, and if you ever write it on one single line, we will punch you. But it could all be on one single line, because logically it is all on one single line. So the lambda function is defined right in there in the middle. Okay, so hopefully that makes sense. That's how you would use parallel.for. There's also a parallel.foreach, which works in a very similar way, and you can look up the syntax of that online. It's nothing terrible. Okay, so let's move on to the other options that we have in here. So we have something called parallel invoke. And parallel invoke allows you to call multiple methods simultaneously, where each one of the methods is going to go off and do its own thing. So the syntax is going to be something like this. You have a method A and a method B, which you would define somewhere else that have their own logic and their own code in them. And you simply say parallel invoke method A and method B. There are a bunch of limitations to this. The first is that the method, it cannot return anything. So method A and method B can't return anything. The second is that no parameters and no return values can come back from them. You can't say method A and pass it 7, method B and pass it 9. It just doesn't work like that. These have to be completely standalone, independent methods that neither take anything in nor return anything back out, which kind of limits the usefulness of it, if we're being completely honest. But, well, it is occasionally useful to do stuff like this, where you just have two things and you know that they can run simultaneously because they have nothing in common. They share nothing. And then the last thing down here is that the order of execution is not guaranteed, and that I would hope makes sense. Anytime that you're dealing with parallel stuff, you have to accept the fact that you have no guarantees on what order things are going to happen in. So keep that in mind when you're doing stuff. Here's another example. This is the for each loop, and that's passing in another little lambda function here, which is what the C is. The data is what's going in, and so you're checking something to see if the C dot value is 10, then you are adding it to something else, whatever. Random example. Okay, so overall, what you should have gotten out of this lecture, and I do realize this was mostly focused on C#. We're going to talk a little bit about Java because it's different next. But what I wanted you to get out of this this lecture so far is that it is possible to do things in parallel. It is not a guarantee that they will execute in any particular order, and there is no guarantee that you will get any performance increase out of it, let alone a 2x or 3x or 4x, depending on how many processors you have. It just depends on how parallelizable the actual job is, what the dependencies between the different parts of your code are, and how much overhead it costs to do the parallelization. There are also lots of problems that you need to think about with regard to blocking. And I mentioned those in the last one, the examples being you have the bank, and it's very important to make sure that two people are not reading and writing. So how do you do that? And the answer is you lock data, and then you pull it back in. You unlock it when you're ready to move on to the next part. Okay, so now I'm going to switch gears, and I'm going to talk about the Java side of the world. I know the C# people are going, yes, he finally did C# plus first. Sorry, Java people. All right, so in the Java world, you're probably going to use something called a ForkJoinPool. To be clear, there are multiple different parallelizations in both languages. Another one that you might run into in Java is streams, and you're welcome to look that one up. A ForkJoinPool works slightly differently than the foreach that we were looking for in the other one. I'm going to flip through these slides because I don't know where these slides came from, but they're not in the normal format, so I'm guessing somebody stole them from somewhere. I'm sure we didn't actually steal them, but I don't know where they came from. All right, so parallel programming, you break it up, you put it into different processors. I think you all understand that. Okay, so a ForkJoinPool has existed since version 1.7, and the cool thing about it is that it will take a task, it will break it up into smaller subtasks. Each of those subtasks are then going to go off and break up into further smaller subtasks and keep breaking up over and over and over again until they are actually individually computable. At that point, you're going to get a result, and the join aspect is it will take the results from each of those subtasks, join them together until you ultimately get your final answer. You might be thinking, haven't we had this lecture before? And the answer is yes. This is recursion. Very specifically, it's just doing the recursion for you in a parallel way. So you have to define how it's going to join the results and how it's going to actually grab the results for you, and then it will go off and do the recursion on multiple different processors. When you were dealing with this before, when you were dealing with recursion, you only ever spoke about it working on a single processor because, quite frankly, we hadn't mentioned any other possibilities. But if you were actually implementing a recursive method in Java, fork join pools would be a good way to do it because you will get a speed increase. And that is indeed what we are going to look at. Okay, I'm flipping through the slides. So Fibonacci is our favorite thing because we love talking about bunnies and what they do in their spare time. So in the Fibonacci sequence, you remember that the sum of every number, every number is the sum of the previous two numbers. And the answer to calculating it in the regular world was if n is less than or equal to 1, i.e. if n is 0 or n is 1, then the answer is 1. Otherwise, you're going to have to calculate what the Fibonacci of n minus 1 was and the Fibonacci of n minus 2 is, get those answers, add them together, and that is your result. And of course, that's going to result in some form of a tree. To get the Fibonacci of 4, you need the Fibonacci of 3 and 2, and to get each of those, you're going to have to go off and compute all the different things until you can finally get an answer. So doing this with a fork join pool, we are going to look at some of the code here. And I didn't put this in Replit, but you could copy and paste this into Replit. These slides are obviously on the website, so you can go grab them, or you can type it from memory if you like. All right, so what's going on here is that you're going to extend a recursive task. So recursive task is an object, and it specifically it's a templated object. It takes in a type, which in this case is going to be an integer because Fibonacci is calculating an integer. If you're going to extend recursive task, there are a couple of quick requirements. The first requirement is that you must override compute. Compute is the method that is actually going to be called to do all of the work. If we look inside of compute down here, you're going to see that it has very common familiar code. As a matter of fact, that's exactly what we did in the previous slide. We're calculating the Fibonacci of n minus 1 and n minus 2, and we're adding them together, except that we're going to put in a fork and we're going to put in a join at the bottom there. All right, so the fork means that finding the Fibonacci of n minus 1 can be forked. All right, let's talk about that word. So you will hear in most languages that fork is an option. What fork means, I'm going to be very careful every time I say that. What fork means is that you normally have one process. At the moment that you fork, it's going to create another process. Think of in a tree, if you're going up the trunk of the tree, that's the word, at some point you're going to fork into all of the different branches, right? And so you might have 3 forks, and then each of them may fork into other branches and so on and so forth. So I want you to think about forking as being a point where you have a fork in the road, right? You're driving and then suddenly the road splits into 2 and you can go left or you can go right. Same thing is happening with a process. You're forking the process into 2 separate processes, and each of them is then going to be able to run on its own. So that's the definition of fork. The definition of join, as we said, is to take the results from 2 things that you have previously forked and put them back together again, which you're doing by adding them in. So that's what's happening down there. All right, so there's a lot of extra junk in here that I wish they didn't put in, where they're taking in parameters to the main method. This is just how you read things off the command line. One of them is what you're taking the Fibonacci of, and then the other one is related to exec time so that it'll actually calculate the time. So you can safely ignore all of this, and you can safely ignore all of this. The only thing that actually matters in here for the purposes of what we're talking about are these 2 lines here. So ForkJoinPool, which is the type of forking that we're doing here, variable name gets new ForkJoinPool. It can take in an optional parameter which specifies how many you actually want. And then the ForkJoin task, which there is a difference that was explained here, a task produces a result, whereas an action does not return a value. So you can either do a task or you can do an action. In this case, we're doing a task because we are going to get back an answer. The task is going to be a new Fibonacci of fib number. All right, and that's going to invoke the Fibonacci method, which will in turn call the compute method when you do the forking. All right, so hopefully that makes some sense. Again, you're not going to have to write anything like this on a test or anything of this depth. There will be at some point later in your career, probably an entire class where you're going to speak a whole lot more about parallelization, forking, pooling of threads and of that. We just wanted to give you a high level version of how it all works so that you're at least familiar with the words. The words should be a thread, multi-threaded application, a process, which that's just a bigger version of a thread, forking, which is how you break off into another process. You don't use the word fork with regard to threads. Threads are create thread, kill thread. Processes are forked generally in most languages. Join, which pushes them back together again, and the idea of parallelization giving you a speed increase, but not necessarily giving you a 2x or 4x or whatever else. So that's the end of today's lecture, and that's the end of all we wanted you to get out of the parallelization section of module number 8, I believe is the current module. So that's it for this week. I will see you guys next week where we will start talking about data structures. I hope you guys are hanging in there. We are almost to Thanksgiving. Have a great week, and I will talk to you all soon.